Hi, I'm Scott from Tutoring.com, and in this video I'm going to show you an example of how to calculate the electric potential from 2-point charges. Electric potential can be really weird. It's kind of a tough concept in this course, but the actual calculations aren't that bad, and my hope is that you'll see fairly quickly from this example that it's really not that bad at all. So we're given two different point charges, and we have to find the electric potential at a certain point P. So I'll write down we're given, I've drawn 2-point charges here, and we have to find the electric potential, and for whatever reason the symbol for that is often V, so capital V at point P. The other thing we have to find, and I'll get to that in the second part, but the other thing that we have to find is what if we put a third charge, Q3, at P, then we have to find the potential energy of that point charge of Q3. So we're given that the positive charge Q1 has a positive 7 microcoulomb charge. The negative charge Q2 has a negative 6 microcoulomb charge. We're also given some information about the sort of topology or the layout here. Point P is located 40 centimeters away from the line that connects Q1 and Q2. Q1 is 30 centimeters above where that line intersects the other line, and Q2 is 40 centimeters below, which means that Q1 and Q2 are 70 centimeters apart. So the first thing we need to do is to find the electric potential at point P. So let's start with that. Now, the electric potential at a given distance from any point charge is equal to, it's actually really simple, K times Q over R. And this is a scalar quantity. There's no vector involved, not a vector. Also, the distance isn't squared. So this looks at first like Coulomb's law, but the R underneath is not squared. One of the nice things about electric potential is that it does follow the rule of superposition. So the electric potentials from a whole bunch of point charges all add up at a certain point. So this is actually fairly easy to calculate, because what we can do is we can just find the electric potential at point P from one charge at a time. So if I'm looking at Q1, which was positive 7 microcoulombs, if I'm going to use V equals KQ over R to find V1 at P, so V1 at P is going to be equal to K times Q1 over R1, then R1 is going to be the straight distance from Q1 to point P. Now, this was a 3, 4, 5 triangle just because I like making math easy. So I know that R1 is going to be 50 centimeters, and it's really easy to show that, so I'll just speed through that right now. All right, so when I substitute in, then I have my 8.99 times 10 to the power of 9, and I hope that your teacher isn't so picky, but I once had a class who just insisted on using 8.99 times 10 to the 9 instead of 9, and so I just developed that habit on my own. Anyway, then we put in Q1 as 7 microcoulombs, or 7 times 10 to the negative 6, and the distance on the bottom, remember, it needs to be in meters, so it's 0.5, and then we find that V1, so that's the electric potential from the first charge at point P, is 125,860 volts. And 1 volt is 1 joule per coulomb, so I can also write that as joules per coulomb. Then the next step is to look at V2. So V2 at point P is going to be equal to K times Q2 over R2. And then if I draw in Q2, draw in point P, now I need to find R2. And this distance is slightly different because I don't have 30 centimeters, so I have to do different math. We have 40 over here, we have 40 over there, so R2 ends up being 56.57 centimeters. Then when I substitute in for V2, I have 8.99 times 10 to the 9 times negative 6 times 10 to the power of negative 6, because Q2 is negative, all divided by R2, which in meters is 0.5657. And when I solve for this, I end up with negative 95,351 volts. So one of the key points with electric potential is that the potential at any point is just the sum of the individual potentials for each source charge at that point. So the potential at point P, Vp, is just the sum. So we have V1 of P plus V2 of P. And the potentials can be positive and negative, and this is not vector math. These are not vectors, which makes it nice and easy. So we just have to substitute the values in. So we have 125,860 is positive, plus, and then we have the negative 95,351. And that gives us a result of just over 30,000. So 30,509 volts. It's a lot more than a AA battery. So therefore, I would round this off. I only gave one significant figure initially, so I would round this to 30 kilovolts. So that's it for part A. For part B, we had to find the electric potential energy of a third point charge that's located at that point. Any point in space has a certain electric potential. At point P, the electric potential is 30 kilovolts. If we put a charge there, we can find the electric potential energy of that charge when it's at that point. And the electric potential energy is given by UE, and we can calculate it if we know the potential. The UE, electric potential energy of a given charge, Q, is just that charge multiplied by the electric potential. V is the electric potential, and the units for that are volts or joules per coulomb, because 1 volt is equal to 1 joule per coulomb. Q is the electric charge, and this is the electric charge which actually has that potential energy. So this ends up being pretty easy to calculate. If we put a 2 microcoulomb charge, so we were given that Q3 is 2 microcoulombs, therefore we can calculate the electric potential energy of charge 3, I'll call that UE3, it's going to be 2 microcoulombs times the electric potential at that point, which was 30 kilovolts, so that's 30 times 10 to the power of 3, which gives us 0.06 joules. And that's the electric potential energy of Q3 at point P. Now there's one last quick thing before I go. Many students get confused between electric potential and electric potential energy, and between the change in electric potential and the change in electric potential energy. So what I've done is I've improved upon and then shared a handout that I used to give to my students, and they seem to like it, that explains what these are and just really tries to highlight the difference between them to make it easier for you. So if you're at all interested, then you can actually download this worksheet, this handout for free if you go to my website, redmondphysicstutoring.com. If you subscribe with your email address, then you'll actually get access to a whole bunch of different things that are available there specifically to help you pass your physics course.